Welcome to the deep dive. Today, we're really cutting through the noise. We're going to bring you the core insights from, well, a huge stack of knowledge on system design.
Yeah, think of it as your express lane to becoming, incredibly well informed on how some of the most complex digital platforms are actually built.
Exactly. We've got a fascinating collection of sources today. We're talking the guts of coding platforms, the real-time pulse of live comments, even the ironclad consistency needed for payment systems.
And what's truly fascinating here, I think, is how these systems that seem so different, a coding site versus a fitness tracker, they actually grapple with very similar fundamental challenges.
Right.
We'll be uncovering those recurring themes, managing scale, ensuring data integrity, keeping things fast, all while navigating those essential trade-offs every engineer has to face.
Our goal is really to give you a structured but maybe surprising analysis. Hopefully you'll have those
Mm.
aha moments that make this whole intricate world of system architecture, well, click into place.
Let's get started.
Okay, so our first major challenge takes us into the world of online coding platforms. If you've ever used something like LeetCode where you can code, submit, get instant feedback, you've experienced quite a feat of engineering. So how do we even begin to build something like that from the ground up? Hashtag tag tag I. Designing a coding platform like LeetCode.
Right. So when you're designing a coding platform, the functional requirements are pretty clear, wouldn't you say?
Yeah, users need to browse problems, pick one,
Exactly. View a list, access specific ones. Then critically, they need to be able to write solutions in multiple languages right there in the browser.
and submit it, and get that immediate feedback pass or fail on the hidden tests.
Immediate feedback is key. And for the competitive element, you absolutely need a live leaderboard showing real-time rankings during contests.
That instant feedback loop is so crucial for learning. Now, beyond what it does, a solid platform needs clear, non-functional requirements too.
Definitely. Availability comes first, right? It's generally more important the site stays up, can accept submissions, even if maybe a leaderboard update takes a fraction of a second longer to show everywhere.
You'd rather have a slightly delayed score than a
Yeah,
completely crashed system, yeah.
for sure. And then there's the absolutely vital piece, isolation and security when running user code. You're executing potentially malicious, arbitrary code.
You gotta keep it sandboxed, prevent it affecting others or the host system.
Precisely. Plus, results need to come back fast within a tight, say, 5-second window. And the system has to scale for big competitions, maybe 100,000 concurrent users.
Okay, 100,000 users. That brings us to capacity estimation. The main target seems to be handling those competition peaks, right?
Yeah, exactly. While average daily load matters, it's being able to handle those sudden, intense surges, that 100,000 user mark that really drives the architecture towards horizontal scaling.
Makes total sense. Be ready for the big moments. Okay, so at the heart of this, what are the core entities we're dealing with?
Pretty straightforward. You've got the problem entity itself. That holds the statement, the test cases, expected outputs, all that.
Okay.
Then you have a submission that stores the user's code, the language they used, and importantly, the results from running against the test cases.
Pass, fail, errors.
Right. And finally, the leaderboard entity, which is all about managing and displaying those competition rankings.
Got it. So problem submission, leaderboard. What about the API, the system interface?
Again, fairly standard. You'll need endpoints for viewing lists of problems, viewing a specific problem's details.
Makes sense.
The submit solution API is obviously key. That's where the user's code comes in. But a critical security point here.
Yeah.
The user main should not be passed in the request body. That needs to be handled securely through the session or authentication tokens. Don't trust the client with that.
Good point. And for the View Live Leaderboard API, same principle.
Exactly. Never pass things like user aid or timestamps and query parameters or the body. Those should always be server-generated or session-based to prevent any kind of tampering and ensure data integrity.
Okay, secure by design. Now, our sources didn't explicitly break out a data flow section, but we can infer it, right?
Yeah, it's pretty much implied in the high-level design. User submits code, it goes to the backend, gets run in a controlled environment, results are stored, feedback goes to the user leaderboard, gets updated. It's a rapid cycle.
Needs to be efficient. So let's talk high-level design. How do the pieces fit together?
Okay, for viewing problems, a NoSQL database like, say, DynamoDB works well. It's good for simple queries, and you can easily nest those test cases as subdocuments within the problem itself.
Convenient. And the coding interface.
You'd leverage something like the Monaco editor, the one PS Code uses, gives you that rich in-browser coding experience with syntax highlighting and all that.
Familiar for users. Now, the really tough part, submitting solutions and getting feedback. How do we handle running arbitrary code safely and quickly?
This is where the core engineering challenge lies. Our sources lay out two main approaches. First, containerization, using Docker.
Okay.
Run user code in isolated Docker containers. You can often reuse them for efficiency, cuts down on startup time.
But the catch.
Well, containers share the host OS kernel, so you need really tight security configurations, strict resource limits, CPU, memory to stop malicious code escaping or hogging resources.
Right. Prevent denial of service or worse. What's the alternative?
Serverless functions, like AWS Lambda, these are managed by the cloud provider, giving you isolated environments per language runtime for each execution.
So less infrastructure management for us.
Definitely. It offloads a lot, but you might face cold start latencies, which could be an issue for that 5-second window requirement. Trade-offs, always trade-offs.
Always. And you mentioned leaderboards earlier. Just querying a database constantly for rankings sounds like a recipe for disaster at scale.
It absolutely is. Which brings us neatly into our deep dives exploring these critical optimizations. Hashtag 8, deep dives.
All right, let's get into the nitty-gritty. First up, that absolutely critical point. Isolation and security of user code. How do you really stop malicious code from breaking out of its sandbox?
This is where you have to be meticulous, layer upon layer. First, a read-only file system for the user code itself. Any output needs to go to temporary directories that get wiped automatically.
Okay, lock down the file system. What else?
Strict CPU and memory bounds. If the user's code goes over the limit, you kill the container. No exceptions. Prevents resource exhaustion.
Like a resource governor.
Exactly. Then, an explicit timeout. Wrap the user code execution. If it doesn't finish within, say, 5 seconds, terminate it. Handles infinite loops, meets latency goals.
Makes sense. Network access.
Gotta limit network access. Disable external calls from within the containers. In AWS, you'd use things like VPC security groups or network ACLs.
Lock outgoing connections.
And for the really hardcore security, you can use kernel features like seccomp. This lets you strictly limit the actual system calls a process is allowed to make. It's like building a very, very strong wall around the code.
Wow, okay. That sounds comprehensive. So code is locked down, but what about keeping that leaderboard flying? 100,000 users hammering it. How do you make it fast?
Yeah, you can't just query the main database every second. The solution for efficient leaderboard fetching is typically using Redis sorted sets combined with periodic polling.
Redis, the in-memory store.
Precisely. It's incredibly fast. When a submission is processed and a score updated, you update both the main database for durability and this Redis sorted set. Redis keeps a real-time sorted list of scores in memory.
And the clients?
Clients pull the server, say every 5 seconds. The server just needs to grab the top end users directly from the Redis sorted set using a command like zarrange. It's blazingly fast, avoids hitting the database for reads. That 5-second interval is usually a good balance for near real-time feel.
Clever. Okay, now back to the overall scale. Scaling for 100,000 users, especially during those competition peaks. What are the key strategies?
The API server itself. That's usually manageable with standard horizontal scaling. Load balancers, add more instances. The real bottleneck is the code execution part.
Running all that submitted code.
Right. So you horizontally scale the language-specific containers or serverless functions. You use auto-scaling groups, triggered by traffic loads, CPU, memory usage, whatever makes sense. This lets you handle the peaks without paying for idle resources all the time.
Dynamic scaling. Makes sense. Are there anything else we can do?
Yes. A really important enhancement, especially for those peaks, is to introduce a message queue like AWS SQS or RabbitMQ. Put it between the API server and the execution workers.
How does that help?
It acts as a buffer. During a massive submission surge, the API server just quickly puts the job onto the queue and tells the user, got it. The execution workers pull jobs off the queue at their own pace. It prevents the execution system from getting totally overwhelmed.
So it decouples the submission from the execution, makes it asynchronous.
Exactly. The user then polls for their results. Plus, it adds resilience. If an execution worker crashes, the message is still safe in the queue and another worker can pick it up. Enables retries.
Nice. Okay, one last headache for LeetCode. Handling test cases across multiple languages. Writing unique tests for Python, Java, C++, say, for every single problem sounds like a maintenance nightmare.
Oh, it absolutely would be. The smart way is language-agnostic test cases. You write one set of test cases per problem
In what format?
in a standardized universal format, like JSON or YAML for input and output data. Then, for each language you support, Python, Java, whatever, you create a test harness.
The harness.
Yeah, a small piece of code specific to that language. Its job is to deserialize the language-agnostic inputs, pass them to the user's submitted code, run the user's code, capture the output, and compare it against the deserialized expected output from the universal test case definition.
So the harness bridges the gap between the universal test case and the specific language.
Precisely. It drastically cuts down on writing and maintaining test cases and ensures consistency across all languages. It's all about abstraction.
Okay, we've just unpacked how individual code runs securely, how leaderboards stay lightning fast. But a totally different, equally massive challenge pops up when you think about comments in a live stream. Millions of people, instant updates.
Yeah.
How does that even work? That brings us to designing something like Facebook's live comments.
Right, a very different beast. The scale and real-time demands are immense. #2, designing Facebook's live comment system. So for live comment system, the functional requirements are all about that dynamic, real-time interaction. Viewers need to be able to post comments on a live video.
Okay, standard enough.
But the critical part is that new comments have to appear in near real time for all the other viewers watching that same stream.
Yeah, that live feeling is everything.
And to provide context, viewers should also be able to load and see comments that were posted before they joined the stream. You need that history.
Makes sense. Okay, non-functional requirements. This is where it gets wild, right? Scale.
Absolutely wild. This system needs to handle millions of concurrent videos and potentially thousands of comments per second per video for popular stream.
Thousands per second per video. Wow.
And because of that scale, availability takes priority over strict consistency. Eventual consistency is usually fine here.
Meaning, it's okay if my comment shows up a fraction of a second later for someone else, as long as the system doesn't fall over.
Exactly. Better slightly delayed than completely unavailable. And the latency goal is tight broadcast comments in less than, say, 200 milliseconds end-to-end to maintain that live feel.
200 meters, okay. So capacity estimation.
Mm-hmm.
It's just massive, right? Millions of videos, thousands of comments per second per video.
It's truly staggering. It's not just the total volume, it's managing those intense bursts across a huge number of independent streams simultaneously. The architecture has to be built for this from the ground up.
It really paints a picture of distributed chaos almost. What are the core entities involved here?
Much simpler than the scale suggests, actually. You've got the user, who can be a viewer, or the broadcaster. You have the live video itself, which acts as the container or topic for the comments. And then you have the actual message posted by a user on a specific live video.
User, live video, comment. Got it. How about the API? What does that look like?
It's focused. To create a comment, a user's client would send a POST request to an endpoint, like comments.livevideoid.
Makes sense. Identifies the video. What about fetching older comments? That history aspect.
For that, you'd use a GE per request, maybe something like comments.livevideoid.cursor last commented in page size 10?
Cursor last commented. So cursor pagination.
Exactly. Cursor pagination is crucial here. It's way more efficient for those infinite scrolling interfaces than traditional offset pagination, especially when new data is constantly being added. It just tells the database, start reading after this specific comment, rather than skip the first X comments.
Much more efficient at scale. Okay, data flow. How does a comment get from one user to all the others in real time?
Okay, so a user posts. Their client sends that POST request to a comment management service.
Right.
That service first persists the comment, usually in a fast, scalable database like DynamoDB. Speed and availability are key here.
Store it first.
Yes. Then, immediately after persistence, that same comment management service uses a real-time mechanism, often server-sent events, SSE, to push that new comment out.
Push it where?
To all the other connected clients who are currently subscribed to watching that specific live videoid, those clients receive the push, add the comment to their feed, and boom, real-time effect.
Okay, so post, persist, push via SSE. What about the high-level design then?
It revolves around that flow. DynamoDB is great for the persistence part scalable, fast writes. For viewing new comments, simple polling just won't cut it at this scale. It would hammer the database. You need that push mechanism like SSE.
Which we'll dive into.
Exactly. And for viewing past comments, that cursor pagination we talked about, often using something like DynamoDB's last evaluated key, is absolutely essential for efficiently handling that infinite scroll. Hashtag tag 8 deep dives.
Okay, let's dive into that real-time comment broadcast. Why do the sources lean towards server-sent events, SSE, instead of, say, WebSockets for this?
It really comes down to the read-to-write ratio. For live comments, you have potentially millions of viewers just reading updates, but far fewer people actually posting comments at any given moment.
So it's very asymmetrical.
Highly asymmetrical. WebSockets are fantastic for balanced two-way communication, but SSE provides a simpler, more lightweight, one-way persistent HTTP connection specifically designed for the server to push updates to the client. It handles these frequent reads efficiently without the overhead of a full duplex WebSocket connection.
Simpler for this use case. Are there any downsides to SSE?
Yeah, a couple. Browsers often have limits on the number of concurrent SSE connections per domain, which could be an issue at extreme scale. And sometimes intermediate proxies or load balancers might terminate idle connections, requiring reconnection logic.
Okay, trade-offs again. Now, the big one. Scaling for millions of concurrent viewers using SSE. If you scale your backend horizontally, viewers watching the same video might connect to different server instances, right?
Exactly. That's the core coordination challenge. User A posts a comment handled by server 1, but how does that comment get pushed to user B who's connected to server 2?
How do you solve that?
Our sources explore a few strategies. One is intelligent routing at the edge using the load balancer.
How would that work?
Option A, consistent hashing at layer 7. The load balancer, like NGINX or Envoy, inspects the live video ID in the request and uses a hashing algorithm to consistently route all viewers for that same video to the same backend server instance.
So everyone watching video X ends up on server 3.
Potentially, yes.
All right.
Option B is a dynamic lookup. The load balancer queries a separate coordination service like Zookeeper, etc., which maintains a real-time map of which server is currently handling which live video ID. More flexible, but adds complexity and another potential point of failure.
Okay, those are routing solutions. What else?
The most commonly recommended approach, especially in interviews, is the pub-sub model.
Publish, subscribe. How does that apply here?
Your real-time messaging servers, the ones maintaining the SSE connections with clients, subscribe to specific topics. These topics usually correspond to the live video ID.
Okay.
When a new comment comes into the comment management service, after persisting it, the service publishes that comment to the relevant topic, the live video ID, in a pub-sub system.
Like Kafka or Redis PubSub.
Exactly. Then, all the real-time messaging servers that are subscribed to that specific video's topic receive the message instantly. Each server then pushes the comment down through the appropriate SSE connections to the clients it's responsible for.
So the PubSub system acts as the broadcast mechanism between the backend servers.
Precisely. It decouples the comment creation from the fan-out to clients.
What about the choice between Kafka and Redis PubSub?
Kafka offers great scalability, fault tolerance, and message persistence, replayability, but potentially slightly higher latency for this kind of real-time push. Redis PubSub is extremely low latency, fire and forget, but offers no persistence. If a subscriber is down, it misses the message. For live comments, the low latency of Redis PubSub is often preferred, accepting the lack of persistence.
So PubSub seems like the most robust way to handle that fan-out across servers.
Generally, yes. It's easier to implement and reason about than complex routing rules or dispatcher services, and it clearly addresses the viewer co-location problem.
Okay, let's pivot now. Let's talk about something absolutely fundamental to almost any modern app: notifications. How do you build a system that reliably delivers messages? Transaction alerts, updates, marketing, come what may. This seems crucial. Hashtag tag 3. Notification service system design.
Yeah, a robust notification service is critical infrastructure. Functionally, its main job is to deliver messages asynchronously. You have publishers sending messages and subscribers receiving them.
And it's usually topic-based, right?
Exactly. A topic-based publish-subscribe model. Messages get categorized by topic, users subscribe to the topics they care about, and it needs to be flexible enough for diverse use cases, critical things like transaction alerts, but also system updates, maybe even marketing messages.
Got it. And the non-functional requirements must be pretty demanding.
Extremely. You need high scalability and reliability above all else. It has to handle potentially massive volumes, maybe bursty traffic, without breaking a sweat. And critically, it needs to guarantee at least once delivery.
Meaning a message might arrive more than once, but it will never get lost.
Precisely. Losing a critical notification is unacceptable. The whole architecture also needs to be horizontally scalable and inherently fault-tolerant. If one part fails, notifications still need to flow.
Okay, at least once is key. Does our source material give specific numbers for capacity estimation here?
Not explicit numbers, no. But the requirements themselves, high scalability or reliability, at least once delivery, strongly imply a system designed for very large scale. Think potentially billions of notifications. The architectural choices, like using message queues and distributed databases, are definitely made with the expectation of handling high throughput and absorbing significant traffic spikes.
So, built for resilience under potentially huge, unpredictable load. What are the core concepts or entities?
It really revolves around topics for categorizing the messages and subscriptions which link users or endpoints to those topics. The messages themselves are, of course, the primary data unit flowing through.
Topics, subscriptions, messages, simple concepts, complex execution. What about the API? How do systems interact with it?
It's typically a straightforward RESTful API you'd likely have. Post topics to create a new topic.
Okay.
To send a notification, a publisher would use post topics, name publish.
Right, push a message to a specific topic.
Then for users or endpoints to sign up, they'd post topics, dad topic name subscribe. This usually kicks off a confirmation workflow.
Like an email confirmation link.
Exactly. Which might involve hitting a GET subscriptions token confirm endpoint with a unique token to finalize the subscription.
Standard confirmation flow. Okay, let's trace the data flow. How does a message get from publisher to subscriber reliably?
It's a multi-stage process designed for decoupling and resilience. Stage 1 is ingestion. A client request hits a load balancer,
Standard stuff.
then goes to a stateless front-end service. This service handles authentication, validates the request, maybe does some basic deduplication using a cache like Redis.
Okay, initial validation, then what?
Stage 2, decoupling and persistence. Once the message is validated, the front-end service doesn't try to deliver it directly. Instead, it publishes the message to a robust message, queue think Kafka or AWS SQS.
The queue again. The backbone.
Exactly. It immediately gets back an acknowledgement from the queue and can return an HTTP 202 accepted to the publisher. The message is now safely and durably stored in the queue, protected from front-end failures and absorbing any traffic spikes.
Smart. So the publisher knows it's been accepted, but delivery is handled later.
Precisely. Stage 3 is processing and dispatch. A pool of worker services, let's call them sender services, constantly pulls the message queue for new messages.
Consumers of the queue.
Right. When a sender picks up a message, it needs to know who to send it to. So it queries a metadata service.
What's in the metadata service?
That service holds all the topic and subscription information which users are subscribed to which topics. It's usually backed by a scalable NoSQL database like Cassandra or DynamoDB and uses heavy caching, Redis again, to provide fast lookups.
So sender gets message, asks metadata service who gets this.
Gets
List of subscribers.
Exactly. Then the sender service creates parallel delivery tasks for each subscriber or group of subscribers and invokes the appropriate downstream delivery mechanism. Could be an email service, an SMS gateway, a push notification service like APNS or FCM.
Handles the actual sending. So the high-level design is really these decoupled microservices talking via a central message queue.
That's the essence of it. You've got the front end for ingestion, the message queue as the durable decoupling backbone, the sender service pool for processing and dispatch, and the metadata service for managing subscriptions, heavily cached. It's an architecture purpose-built for scale, resilience, and handling asynchronous workflows. #8 deep dives.
Okay, let's dive deeper. The storage strategy is crucial here. For that temporary message storage, that backbone queue, why Kafka specifically?
Apache Kafka is often highlighted because it's really optimized for this kind of high-throughput, durable streaming workload. It offers excellent durability through replication across multiple brokers. It supports partitioning, which allows multiple sender service instances to consume in parallel, boosting throughput. and its persistence is vital for enabling retries if delivery fails. While other queues work, Kafka's features make it a very strong contender for a high-scale notification system, arguably superior to using a generic NoSQL database for the queue itself.
Makes sense. And for the metadata database, the topic and subscription info.
There, a partitioned NoSQL solution like Apache Cassandra or Amazon DynamoDB is a perfect fit. You can shard the data effectively by topic name or subscriber to achieve horizontal scalability. And as we mentioned, putting a caching layer, like Redis, in front of this database within the metadata service is critical to minimize database hits and keep lookups super fast.
Okay, storage covered. Now, how does this system actually handle failures and retries to guarantee that at least once delivery promise?
It's handled at multiple points. If the publisher fails to initially publish to the queue, the front-end service should retry. Even the original client publishing might have its own retry logic.
Okay, retries on the way in. What about on the way out? Queue to subscriber.
This is where the message queue shines. If a sender service instance picks up a message, tries to deliver it but fails, maybe the downstream SMS gateway is down, the message doesn't get deleted from the queue immediately. It remains invisible for a visibility timeout, then becomes available again for another sender instance to pick up and retry.
The queue manages the retry state. What if a message keeps failing? A poison pill message.
Good point. You don't want one bad message blocking the queue forever. That's where the dead letter queue, DLQ, comes in. After a certain number of failed delivery attempts, a configured retry limit, the message is moved from the main queue to a separate DLQ. This gets it out of the way, allowing other messages to flow, and the messages in the DLQ can be inspected later to figure out what went wrong.
Clever way to handle persistent failures. What about slow subscribers? If one email server is responding slowly, does it slow down everything else?
No, and that's the beauty of the parallel delivery tasks. When the sender service gets the list of subscribers, it typically spins up separate tasks or uses an asynchronous framework to handle delivery to different endpoints or batches of endpoints. So one slow SMS delivery won't block push notifications or emails for other users. It maintains overall throughput.
Nice isolation. So, wrapping up the notification service, what are the absolute key system requirements and solutions that make it robust?
Okay, boiling it down. Scalability is achieved through stateless, horizontally scalable components, front-end senders, and partitioned data storage, MQ partitions, NoSQL sharding. High availability comes from deploying multiple instances across different availability zones, plus the inherent replication in the MQ and NoSQL database. Durability is guaranteed by persisting messages in the MQ immediately upon receipt and only deleting them after successful delivery is confirmed, or they're moved to DLQ. Security involves TLS for data in transit, encryption at rest, and proper authentication authorization at the API endpoints. And finally, monitoring is essential comprehensive metrics on latency, throughput, error rates from all services, plus detailed audit logs for tracking message status and API usage, usually fed into a separate logging and analysis pipeline.
Okay, that's a solid foundation. Let's switch gears completely now. Let's take a breath from designing whole systems and dive into something maybe a bit more fundamental but equally important. The actual language of system design, the numbers. This is where you get those cheat codes for quick estimations, right?
Exactly. This next source isn't a system design problem itself. It's more like a reference guide, a conversion cheat sheet. So you won't find functional requirements, non-functional requirements, entities, APIs, or a high-level design for the cheat sheet.
Right, it's the toolkit, not the blueprint. It provides the raw ingredients, the numbers, the metrics that we use when we're discussing all those other aspects like capacity estimation or choosing technologies.
Precisely. It's the vocabulary we need to speak fluently about scale and performance. Hashtag, tag, free estimation.
And this is where this source really shines, providing those crucial numbers for capacity estimation. Let's start with data unit storage, bandwidth.
Yeah, the basics but essential. 1 kilobyte KB is 1024 bytes. Remember the binary 1024, not 1000. 1 megabyte is 1024 KB.
1 gigabyte GB is 1024 gigabytes, which is approximately 1 billion bytes, a useful mental shortcut.
Good one. 1 terabyte TB is 1024 megabyte, and 1 petabyte PB is 1024 DB. Just knowing these orders of magnitude is crucial.
Absolutely. And then there are the number of units we use for users, operations, money.
Simple powers of 10, but good to have handy. 1,000, 1 million, 1 billion, 1 billion tenure, and 1 trillion tenor words. Helps visualize scale quickly.
Okay, now for the really quick mental conversions that are super handy, especially in interviews, you mentioned 1 gigabit, 1 billion bytes.
Right, and 1 TB is roughly 1,000 gigabit, which translates to about 8 trillion bits, since 1 byte equals 8 bits.
Ah, the bits versus bytes conversion, important for network speeds, like 1 GBps, gigabytes per second, is roughly 8 gigabits per second, right?
Exactly. And conversely, 1 GB piece is about 125 millibits, 1008, useful for translating network bandwidth into download speeds.
Definitely. And what about translating daily traffic into per second rates?
Key calculation. Request per second RPS equals request per day divided by 86,400, which is 24 hours, 60 minutes, 60 seconds.
So a quick rule of thumb.
1 million requests per day is roughly 11.6 RPS, call it 12 RPS, and 100 million requests per day is about 1157 RPS, call it 1200 RPS. These give you an instant feel for the intensity of the load, hashtag tag 8. Deep dives.
So the deep dive section for this source isn't about a specific system, but more about system components, key metrics, and scale triggers. This feels super important understanding when typical components start to strain.
Exactly. This is about knowing the limits and the warning signs. Let's take caching systems like Redis or Memcached.
Okay, what are the typical metrics?
You're looking at very low latency, often around 1 millisecond or even sub-millisecond. Throughput can be very high, 100,000 plus operations per second per node or shard, and they are typically memory bound, with instances scaling up to maybe a terabyte of RAM.
And when do you need to scale your cache? What are the triggers?
Common triggers include cache hit rate dropping below 80%, meaning you're missing a cache too often, average latency climbing above 1 millisecond, memory usage consistently over 80%, or observing high cache churn or thrashing, frequent evictions and replacements. These indicate the cache isn't keeping up or isn't sized right.
Got it. What about databases, both SQL and NoSQL?
Metrics here vary widely, but high-end systems can handle maybe up to 50,000 transactions per second, TPS. Read latency, especially if data is cached in the DB's buffer pool, can be sub 5 milliseconds. Storage capacity can easily go into 64 terabytes and beyond.
And the scaling triggers for databases.
You'd look at scaling options if your write throughput consistently exceeds maybe 10,000 TPS, if read latency for uncached data goes above 5 milliseconds regularly, or if you have requirements for geographic distribution necessitating replicas or sharding across regions.
Okay. How about standard application servers? The workhorses handling requests.
They can typically handle 100,000 plus concurrent connections per instance. Hardware-wise, you might see 864 CPU cores running at 2 to 4 gigahertz, with 64 512 gigahertz of RAM being pretty standard, though high-end servers can go up to 2 terabytes or more.
And when do you add more app servers?
Scale triggers include CPU utilization consistently above 70%, response latency exceeding your SLA service level agreement targets, the number of connections approaching that 100K limit per instance, or memory usage consistently above 80%. These indicate the servers are becoming overloaded.
Makes sense. Finally, message queues like Kafka or RabbitMQ.
These are built for throughput. Kafka brokers, for instance, can handle up to 1 million messages per second individually, with clusters handling much more. End-to-end latency can be very low, sub 5 milliseconds in optimal conditions. Storage per broker can reach 50 terabytes.
Impressive numbers. What are the scaling triggers for message queues?
You'd look at scaling your cluster or adding partitions if throughput per broker nears its practical limit, maybe 800K messages a sec as a threshold. If the total partition count in a Kafka cluster gets very high, maybe approaching 200,000. Or crucially, if you see growing consumer lag, meaning your consumers just can't process messages as fast as they're arriving, that's a sure sign you need more consumers or more partitions.
Okay, armed with those numbers, let's tackle another classic system. Think about eBay auctions changed how people buy and sell online. Bids flying in, needing real-time updates, everyone seeing the same price. What does it take to build an online auction platform? Hashtag tag DeepinEV. Designing an online auction platform like eBay.
Right, an online auction platform. The functional requirements are pretty intuitive, I think. Users need to be able to post items for auction, right? Setting things like a starting price and end date.
The basics of listing an item.
Then, critically, other users need to be able to bid on those items, and the system has to enforce the rule. A new bid is only accepted if it's higher than the current highest bid.
The core auction mechanic.
And finally, users need to be able to view an auction's details, including seeing that current highest bid, ideally in real time, so they know what they need to bid.
Makes sense. Now, the non-functional side must be tricky here, especially with money involved implicitly.
Very tricky. First and foremost, you need strong consistency for bids. Everyone viewing the auction must see the identical highest bid at the same time. Any divergence here destroys trust completely.
Absolutely critical.
What else? Fault tolerance and durability. You absolutely cannot lose a bid. A placed bid must be reliably recorded and processed. Dropping bids is a catastrophic failure.
Non-negotiable.
You also need to display that current highest bid in real time or very close to it to make the auction dynamic. And thinking about scale, the system needs to support potentially millions of concurrent auctions, say 10 million concurrent auctions as a target.
10 million auctions happening at once. That's a capacity estimation target driving the design, though.
Exactly. That number implies a significant volume of concurrent reads, people viewing auctions and writes, people placing bids, all while maintaining that strong consistency and real-time feel. It pushes you towards distributed, highly performant solutions.
Got it. So what are the core entities we're modeling here?
We have the auction entity itself, having details like the starting price, the end date, maybe the current highest bid ID, though maybe not the price itself directly. We'll come back to that.
Okay.
Then the item being optioned, its name, description, image. It's often a good idea to normalize this, make it a separate entity from the option. Why? For reusability, easier updates, maybe item-specific features later.
Good point. Separating auction mechanics from item details.
Yeah.
What else?
The bid. This represents a specific bid event, the amount, the timestamp, the user who placed it, and which auction it belongs to.
And finally,
The user, of course, someone who starts an auction or places a bid.
auction, item, bid, user. Clear. What about the API for interacting with this?
Fairly standard RESTful stuff. To create a new auction listing, a POST auctions request, sending the details, getting the created auction back.
Right.
To place a bid on a specific auction, a POST auctions.auctionedbids, sending the bid amount and user info via auth.
Targets a specific auction.
And to view the details of an auction, a GET auctions.auctionid, which would return the auction info, the item details, and likely the current highest bid information.
Makes sense. Okay, let's trace the data flow. How does listing an item or placing a bid actually happen?
Okay, posting an auction. Client sends POST auctions, hits an API gateway routes to an auction service, validates the data, stores the auction and item data in the database. Pretty standard create operation.
Simple enough. What about placing a bid? This seems more complex due to the consistency requirement.
It is. Client sends POST auctions.auctionedbids-API gateway bidding service. Now, this service first needs to query the database to find the current highest bid for that auctioned.
Check the current state.
Right. It validates if the new bid is higher. If yes, it stores the bid. Now, here's a crucial design choice mentioned in the sources. You should store all bids in a dedicated bids table linked by auctioned.
As opposed to
just overwriting a max bid price field directly on the main auction record.
Why is storing all bids better?
It preserves a complete audit trail. This is vital for data integrity, resolving disputes, did my bid register, and for later analysis. You always have the full history. The current highest bid can be derived or stored separately, but the raw bids are sacred.
That makes a lot of sense. Don't lose the history.
Okay.
And viewing an auction.
Initial view is a simple GET auctions.auctionid. But to keep the max bid price updated, you can't just rely on the user refreshing. You'd typically use polling every few seconds, or ideally a push mechanism to prevent showing stale data.
Leads us to the high-level design. What are the main building blocks?
You'd likely have dedicated microservices, maybe an auction management service, and a separate bidding service, given the different concerns.
Okay.
These services interact with a central database. Given the strong consistency requirement for bids, a relational database, like Postgres, is often a good choice here, perhaps sharded later for scale.
And the real-time updates.
That's where techniques like SSE or WebSockets come in, which we'll get into in the deep dives, building on the initial JGT request, #tag8 deep dives.
Okay, let's dive in. First, ensuring strong consistency for bids. This is non-negotiable. The sources mention optimistic concurrency control, OCC. How does that work in practice here?
OCC is a great fit because most of the time, bids don't conflict simultaneously. So, when a user places a bid, the system reads the current auction data, specifically noting the current highest bid amount or maybe a version number.
Okay, get the current state.
2, it validates the new incoming bid, is it actually higher?
Basic check.
Then, it attempts to update the auction record, for example, update the current highest bidded or increment a version number, but with a condition. only succeed if the value read in step 1 hasn't changed in the meantime.
Like a compare and swap.
Exactly. If the update succeeds, it means no one else snuck in a higher bid, so you then write the new bid record to the bids table. If the update fails because the condition wasn't met, it means someone else did bid higher. So you abort, reread the auction state, and retry the process from step 1.
So it avoids locking, but ensures only valid sequential higher bids get accepted.
Precisely. It's efficient when conflicts are rare, which is often true for bids until the very last seconds of an auction.
Makes sense. Now, ensuring fault tolerance and durability. We said losing a bid is unacceptable. How do we guarantee that?
The classic solution here, again, is a message queue, like Kafka or RabbitMQ.
Using a queue for bids, how does that work?
When a user submits a bid via the API, the bidding service doesn't immediately try to process it and write to the database. Instead, its first action is to write the bid event to the message queue.
Write it to Kafka first.
Yes. Once Kafka acknowledges receipt, the API can respond to the user, "Your bid has been received." The bid is now durably stored in the queue. Even if the bidding service processing logic crashes right after, the bid isn't lost.
Durability up front.
Exactly. The queue also acts as a buffer. If there's a sudden flood of bids, the queue absorbs them, preventing the database or processing logic from being overwhelmed and potentially dropping bids or crashing. Kafka specifically can also guarantee ordering within a partition, for example, for a specific auction, which is helpful.
So the flow becomes user bids, API, write to Kafka. Kafka acts order later. Bid service consumes from Kafka processes, using OCC maybe. Rets to database.
That's the reliable flow. The bid remains safely in Kafka if the consumer service fails, allowing for retries.
Very robust. Okay, finally, displaying the current highest bid in real time. Polling works, but isn't ideal. What's the push-based approach?
Server-sent events, SSE, is often a good fit here, similar to the live comments scenario because it's mostly unidirectional server pushing updates to the client.
So the browser opens an SSE connection when viewing an auction.
Exactly. The server maintains a mapping of active SSE connections for each auction ID. When a new bid is successfully processed after the OCC check and DB write, the bidding service, or a related notification service, finds all active connections for that auction and pushes the new highest bid information down through those SSE channels.
Pushing the update instantly. What about the scaling challenge if different users are connected to different servers?
Same problem as live comments, same solution. A pub sub system. When a new highest bid is confirmed on server A, it publishes that update to a central pub sub topic, for example, using Redis pub sub or even Kafka.
Oh.
All other servers handling SSE connections that have clients interested in that specific option are subscribed to that topic. They receive the update via PubSub and then push it down to their respective connected clients via SSE.
So PubSub coordinates the broadcast between the backend servers handling the SSE connections.
Precisely. Combined with auto-scaling of the SSE handling servers, this allows you to deliver real-time bid updates efficiently, even with millions of concurrent auctions and viewers.
Wow. Okay. Options are complex. Now, if we connect this to the absolute lifeblood of the digital economy, financial transactions, building something like Stripe, that seems like next-level complexity in terms of security, consistency, scalability. Let's dive into that. Hashtag tag VSI, payment system design, Stripe-like.
Yeah, payment systems are definitely high stakes. Functionally, what does a system like Stripe need to do? Merchants need to initiate payment requests, right? Charge their customers.
The core function, take money.
Users, the customers, need to be able to pay, typically using credit or debit cards.
Okay.
And merchants need visibility. They need to see real-time status updates for their payments. Is it pending? Did it succeed? Did it fail? That feedback loop is crucial for business operations.
Absolutely.
Okay.
Non-functional requirements. I imagine these are incredibly strict.
Paramount. Security is number one. Absolutely non-negotiable when dealing with sensitive financial data like card numbers. Breaches are catastrophic.
Got it. Security first.
Then, strong consistency. Financial transactions demand it. You cannot have discrepancies, double charges, incorrect statuses. Data integrity must be perfect.
No room for error.
Durability is also key. You cannot lose transaction data, ever. Every charge, every refund, every status change must be reliably stored.
Makes sense. And scale.
Massively scalable. These systems need to handle huge transaction volumes. potentially 10,000 plus transactions per second, TPS, and they often face very bursty traffic patterns, like during sales events.
10,000 financial transactions per second.
Yeah.
That's the capacity target driving this design.
Yes, that 10K plus TPS figure immediately tells you this needs an architecture designed for extreme throughput, resilience under bursty loads, and maintaining that critical consistency and security throughout.
It sets a very high bar. What are the core entities in a payment system?
You've got the merchant information about the business using the platform, their identity, bank details, API keys for integration.
Okay, the seller.
Then the payment. This represents the overall payment request or intent, tracking its entire lifecycle from creation through to success or failure. It's like the container for the financial operation.
The overall goal.
And then the transaction. This represents an actual charge or refund event against a specific payment method. It encodes the amount, currency, status, pending, succeeded, failed, timestamps, and links back to the payment entity. A single payment might have multiple transactions, for example, an initial charge, then a partial refund.
Merchant, payment, transaction, clear separation. What about the API? How do merchants interact?
It starts with a POST request, typically to create a payment intent. Now, the crucial part, accepting and processing the actual payment. The API here must use secure tokenization.
Tokenization.
Meaning the merchant's backend never sees or handles the raw credit card number directly. The sensitive details are exchanged for a secure token, usually via a client-side SDK or a secure iframe, which is safe to send to the backend.
Keeps the raw card data away from the merchant system. Big security win.
Huge. Reduces their PCI compliance scope dramatically. Merchants can also get the status of a payment. And a really important mechanism is webhooks.
Webhooks. How do they work here?
Merchants provide a callback URL. When the status of a payment changes, for example, from pending to succeeded, the payment system automatically sends a notification, a POST request, to that merchant's URL with the updated status. It's push-based, server-to-server communication.
So the merchant gets notified instantly instead of having to pull constantly.
Exactly. Much more efficient and real-time.
Okay, data flow.
Yeah.
How does a payment actually get processed?
It's a multi-step, often asynchronous process. First, the payment request. Merchant initiates, payment service creates a payment record in the database. Status pending. No actual money movement yet, just recording the intent.
Got it. Intent recorded. Now the card part.
Card processing. The merchant server sends the tokenized card details, never raw, to a dedicated transaction service. This service then interacts with an external payment gateway.
What's the payment gateway?
That's the bridge to the actual private payment networks, Visa, MasterCard, etc. The gateway handles the complex authorization requests, talks to the banks, gets an initial response, approved, declined, and sends that back to our transaction service. But it doesn't stop there.
Why not?
Because payment processing is inherently asynchronous. The initial authorization might be quick, but the actual settlement, money moving, fraud checks, potential chargebacks, these can take minutes, hours, even days. The gateway listens for callbacks from the networks about these later events. Our system has to manage the payment and transaction state throughout this potentially long life cycle.
Wow, okay. So it's not just a quick request response, it's managing long-running state. How do merchants get updates?
The payment service can query the database for the current status if the merchant asks via the API, but webhooks are the primary way merchants get push notifications about those asynchronous state changes, like settlement confirmed or a chargeback initiated.
Makes sense.
Wow.
So high-level design.
It's fundamentally built on microservices. A payment service managing payment lifecycle state, a transaction service handling transaction records, tokenization, interacting with the gateway, and the payment gateway component, the external interface.
Okay.
These interact with a central database storing all the critical data, payments, transactions, merchant info, API keys. And the entire design has to embrace asynchronous processing because the external payment networks operate that way. Robust state management is absolutely key. #8 deep dives.
All right, let's get into the deep dives for payments. System security is paramount. How do you ensure API requests are authentic and crucially protect that card data?
Security is multi-layered. First, request signing. API requests between the merchant and the payment system must be cryptographically signed. The merchant uses their private secret key to create a signature based on the request details, often including a timestamp and a nonce, a unique number, to prevent replay attacks. The payment system uses the merchant's public API key to verify the signature. This ensures authenticity and integrity.
Okay, secures the communication. But what about the card data itself? You mentioned tokenization.
Yes, and the iframe solution is a common and effective way to achieve this. The payment system provides an iframe that the merchant embeds on their checkout page. This iframe is served directly from the payment system's own highly secure PCI-compliant domain.
Ah, so the card number field isn't actually part of the merchant's page.
Exactly. It's in a sandboxed iframe from a different domain. The customer types their card details into the iframe. JavaScript provided by the payment system, running within the iframe or securely communicating with it, immediately encrypts this data client-side using a public key before it even leaves the customer's browser to go anywhere.
So the raw card number never even touches the merchant's server infrastructure.
Never. The merchant only ever receives back a non-reversible token representing the card details. They use this token in API calls. This massively reduces the merchant's PCI DSS compliance burden and keeps the sensitive data locked down within the payment provider's secure environment.
That's incredibly clever and secure. Okay, next challenge. Strong consistency for financial transactions. How do you guarantee this, especially when dealing with those asynchronous external networks?
It requires tackling consistency on two fronts. First, internal consistency within our own system's database. Here you rely on traditional database transactions with full A-to-D properties: atomicity, consistency, isolation, durability. When processing a payment update, you'd update the payments table and the transactions table together in a single atomic database transaction. Using synchronous replication for your database ensures all replicas have the same consistent view quickly.
Okay, standard ACID for internal state. What about external consistency, making sure our system state matches the reality of the external payment networks?
This is harder. One powerful approach mentioned in sources is using an event sourcing architecture. Instead of just storing the current state, you record every single state change as an immutable event in a chronological log.
Like an audit log of everything that happened.
Exactly. Kafka is often used as this immutable transaction log. The payment and transaction services produce events, e.g., payment created, authorization succeeded, settlement received. Dedicated consumer services read these events and update read-optimized database tables that represent the current state.
What's the benefit?
If your read database ever gets corrupted or inconsistent, you can rebuild its entire state perfectly by simply replaying the event log from Kafka from the beginning. It provides ultimate auditability and recoverability.
Wow, okay. Is there anything else for external consistency?
Yes, you also need a reconciliation service. This service runs periodically, e.g. daily, and actively compares our system's transaction records against reports or APIs provided by the external payment networks. If it finds discrepancies, e.g. we think a payment succeeded but the network says it failed, it generates new internal events to trigger corrective actions and align the state.
Proactive checking and correction. Makes sense. Okay, scalability. How do you handle 10,000 plus TPS?
On the server side, all the core services, payment, transaction, should be stateless so they can be scaled horizontally behind load balancers. Just add more instances as needed.
Standard web service scaling. What about the data layer? Kafka.
Kafka itself is designed for massive scale, capable of millions of messages per second at the cluster level. To handle 10K TPS reliably, you'd need multiple partitions within your topics, maybe 3 to 5 partitions, as each partition can typically handle around 5,000 and 10,000 messages per second, providing both throughput and fault tolerance.
Okay, partition Kafka appropriately. What about the database holding the payments and transactions? 10K writes per second is significant.
It is. Several strategies here. First, data tiering archiving. You probably don't need instant access to transactions from 5 years ago. Move older data, we've gone 3 to 6 months, to cheaper, slower cold storage like Amazon S3, keeping the active database smaller and faster.
Keep the hot data hot.
Right. For read scaling, implement database read replicas, many status checks or read operations. Also use a caching layer, read as memcached, for frequently accessed data, like the status of recent payments.
Cache recent stuff. What if write volume itself becomes the bottleneck?
That's when you need to consider write scaling, typically through database sharding. You could partition the data horizontally, perhaps sharding the payments and transactions tables by merchanted, or maybe using time-based partitioning if queries often filter by date range. Sharding adds complexity, but is often necessary at this scale.
Sharding as the ultimate write scaling tool. Okay, finally, you mentioned webhook support. How does that technically work for merchants?
It's pretty simple conceptually. When a merchant integrates, they provide our payment system with two things via our API or dashboard. One, a callback URL. This is the endpoint on their server that our system will send HTTP POS2 requests into. Two, A list of subscribed events. They tell us which types of events they care about, e.g., payment.succeeded, payment.failed, chargeback.created.
So they choose what they want to be notified about.
Exactly. Then, whenever one of those subscribed events occurs within our payment system for that merchant, our system automatically constructs a notification payload, usually JSON, containing details about the event, and sends an HTTP PUST request to the merchant's registered callback URL.
Push, not pull.
Right. It eliminates the need for the merchant to constantly pull our API asking anything new, making it much more efficient and providing real-time updates.
Okay, that was deep. Payment systems are complex beasts. But all this talk about handling high traffic, like 10K TPS or bursts, raises another critical question. How do you prevent one misbehaving client or just a sudden legitimate surge from completely overdumbing your system and taking it down for everyone? That's where rate limiting comes in, right? It's like the bouncer for your API. Hashtag tag 7, rate limiter system design.
Exactly. A rate limiter acts as that crucial gatekeeper. Functionally, its job is pretty simple on the surface. First, it needs to control the rate of incoming requests from any given client, identified by IP, API key, user ID, whatever.
So limits per client.
Right. And second, if a client exceeds their defined threshold, the rate limiter must reject or throttle those excess requests. Usually returns an HTTP 429 too many requests error.
Don't let them flood the system.
Precisely. Prevent one noisy neighbor from ruining the party for everyone else.
Okay, so the non-functional requirements naturally follow from that.
They do. The primary goals are system stability and fairness. It ensures resources are shared equitably and prevents overload. To do its job effectively, the rate limiter itself needs high performance. It shouldn't add significant latency. Scalability, it has to handle the full ingress traffic rate, and fault tolerance.
Because if the rate limiter goes down,
then you have no protection. Or worse, if it fails closed, it blocks everyone.
Right. So capacity estimation for a rate limiter, it needs to handle the peak request rate of the entire system it's protecting, essentially.
Yes, and potentially more, as it might be checking multiple rules per request. The sources emphasize needing very high throughput, particularly pointing to the performance of the backing store, like Redis. We saw those numbers earlier, clustered Redis handling hundreds of thousands, even millions of operations per second with low latency. The rate limiter needs to leverage that kind of speed.
So it's not just the application's TPS, but the rate limiting check TPS that matters here.
Yeah.
Got it. What are the core entities?
Very simple, actually. You have the client, however you identify them, IP address, API key, client ID.
The entity being limited.
And then you have the data structure used to track their usage. The most common one discussed is the token bucket. For each client, you maintain a conceptual bucket holding their current tokens and the last refilled timestamp.
Client and token bucket. Okay. What about the API? Is it a service people call directly?
Not usually, no. A rate limiter typically functions as middleware or a sidecar service. Your actual application servers, before processing an incoming request, make a quick, lightweight internal network call, maybe gRPC, to the rate limiter service.
So it's an internal check, not a public API.
Right. The rate limiter service tells the application server allow or deny, and the application server acts accordingly. It's designed to be very fast and integrated into the request path.
Okay, let's trace that data flow then. Request comes into the application server.
Server identifies the client. Before doing any real work, it makes an atomic call to the rate limiter's data store, which is usually a centralized Redis instance.
Atomic is key here, right, to prevent race conditions.
Absolutely critical. If two requests arrive at nearly the same time, you can't have them both read the token count, both decide they have enough tokens, and both decrement, using two tokens when only one was available. Atomicity prevents this. This is often achieved by sending a Lua script directly to Redis.
Why?
Redis can execute Lua scripts atomically. So a single script can perform the entire check and decrement logic. Get the current tokens and timestamp for the client, calculate how many tokens should have been refilled since the last check, add the refilled tokens up to the bucket max, check if at least one token is available. If yes, decrement the count by one and return allow. If no, just return throttle, all in one indivisible operation.
Very neat. Prevents race conditions entirely.
Exactly. The application server gets back the allow or throttle response. If it's allow, it proceeds with processing the request. If it's throttle, it immediately returns that HTTP 429 error to the client.
Okay, so the high-level design revolves around this token bucket algorithm in Redis.
That's the core. The token bucket algorithm itself is flexible. Each client gets a bucket defined by a bucket size, maximum number of tokens it can hold, representing the max allowed burst of requests, and a refill rate, How many tokens are added back per second, representing the sustained allowed rate? A request consumes 1 token if available. Tokens are constantly added back at the refill rate up to the bucket size. It allows short bursts while enforcing an average rate over time.
Makes sense.
And deployment.
Well, you could integrate it as a library within your application, lowest latency but language specific. For distributed systems, a sidecar daemon service is more common. It runs as a separate process, maybe on the same host or nearby, interacts with the central Redis, and is language agnostic. Your apps just talk to it over the network.
Decoupled and reusable. A simple single-node rate limiter would just use an in-memory hash map, but that clearly doesn't work in a distributed setup.
Right, hence the need for the centralized store like Redis. #8. Deep dives. Okay, let's dive into the distributed rate limiter specifics. The main challenge is consistency, right? Requests from the same client hit different app servers, but they all need to decrement the same token count accurately.
Exactly. You need a shared, consistent, low-latency source of truth for each client's token bucket. And the solution, as we've established, is that centralized high-performance key-value store, with Redis being the prime candidate.
And why Redis again specifically?
3 key reasons. 1, speed. It's in memory, making the read, modify, write operation extremely fast, minimizing added latency to requests. 2, atomicity. Redis provides mechanisms like Lua scripting or atomic commands like INCR or INCRBY that guarantee the check and decrement operation happens indivisibly, preventing those critical race conditions. 3, scalability. Redis can be clustered to handle very high throughput, ensuring the rate limiter itself doesn't become the bottleneck.
Speed, atomicity, scalability. Makes Redis ideal. Now, what about managing the actual rules? You might have different limits for different users or different API endpoints. You can't hard code that.
Absolutely not. The rate limiting rules themselves, FreeG, client X gets 100 requests minute on the search endpoint, free tier users get 10 requests second globally, need to be managed dynamically.
So where are they stored?
Typically, the rules are stored in a persistent database. Could be PostgreSQL, DynamoDB, whatever fits. There's usually a configuration service with a UI or API that allows administrators to define and update these rules.
Okay, rules in a database. But querying the database on every single incoming request to check the rule sounds slow.
It would be. So the trick is caching. Each application server, or the rate limiter sidecar, runs a small background agent. This agent periodically pulls the configuration service or the rules database, fetches the latest set of rules, and caches them locally in memory.
Ah, so the check against the rule happens from local memory cache.
Yes. When a request comes in, the application server quickly looks up the relevant rule in its local cache, determines the parameters, bucket size, refill rate, and the key to use in Redis, for example, ratelimit.clientIDA.endpoint, and then makes the fast atomic call to Redis using those parameters. This avoids hitting the rules database on every request, keeping the overhead extremely low.
Very efficient. Okay, what are some other key considerations or trade-offs when building a production rate limiter?
Fault tolerance is a big one. What happens if the central Redis cluster goes down? You generally want the system to fail open.
Fail open, meaning allow requests through without rate limiting.
Yes. Failing closed, denying all traffic because the rate limiter is down, is usually much worse for overall system availability.
Yeah.
It's often better to temporarily lose rate limiting protection than to take the entire site offline. So if the call to Redis times out or fails, the application server should probably just allow the request.
Prioritize availability. Makes sense. What else?
There's a trade-off between accuracy and performance. Due to network latency between app servers and Redis and potential clock skew, perfect accuracy might be impossible. You might occasionally allow 1 or 2 requests over the limit. This slight inaccuracy is generally considered an acceptable trade-off for maintaining high performance and low latency. Strict enforcement might require slower, more coordinated mechanisms.
Good point. Perfect accuracy isn't always the goal. Memory.
Memory efficiency in Redis is important. You could have millions of clients, each with a token bucket entry. Using Redis's time to live (TTL) feature is crucial. Set a TTL on each client's rate limiting key. So if a client is inactive for a while, their entry automatically expires and gets evicted from Redis, freeing up memory.
Smart cleanup. And finally, how should clients behave when they do get rate limited?
This is important client-side behavior. When a client receives an HTTP 429 response, they shouldn't just immediately retry hammering the server. They should implement an exponential backoff with jitter retry strategy.
Meaning wait longer between retries and add randomness.
Exactly. Wait 1 second, then 2, then 4, then 8, etc., and add a small random amount of time to each delay. This prevents thousands of throttled clients from all retrying at the exact same second, which could cause a thundering herd problem and overwhelm the system again as soon as limits allow. Polite clients are essential for system stability.
Exponential back-off with jitter. Good tip.
Hmm.
Okay, connecting this back to complex systems. Let's think about stock trading. Platforms like Robinhood. It's not just showing numbers, it's about lightning-fast price updates, ironclad consistency for orders, absolutely zero tolerance for errors. How on earth do you build that?
Yeah, stock trading platforms are another level of demanding. Functionally, what do they need to do? Core requirement: display live stock prices to users, constantly updating.
Real-time market data is essential.
And then order management. Users need to be able to create orders, market orders, buy, sell at current price, limit orders, buy, sell at a specific price or better. They need to be able to cancel pending orders, and they need to view the status of all their existing orders.
Create, cancel, view orders. Got it. Non-functional requirements must be intense here.
Extremely. Strong consistency is absolutely paramount for order management. The state of an order, pending, filled, canceled, must be accurate and consistent across the entire system. Financial transactions are involved.
No eventual consistency allowed for orders.
Definitely not. Low latency is also critical. Price updates need to be near real-time, and order placements should ideally confirm in well under, say, 200 milliseconds. Speed matters in trading.
Milliseconds count. Scale.
Huge scale potential. Sources estimate needing to support maybe 20 million daily active users, DAU. This could translate to 100 million trades per day, which averages around 1,000 trades per second, but with peaks easily hitting 10,000 trades per second. And you need to track data for maybe 10,000 different stock symbols.
Wow. 10K trades per second peak.
Plus, efficiency is important. Connecting directly to stock exchanges for live data feeds is expensive, so you want to minimize those connections and efficiently distribute the data internally. And reliability is non-negotiable. The system must handle failures gracefully without ever losing or mismanaging an order state.
Okay, let's quantify that scale based on the capacity estimation numbers.
Right. Users trades, 20 MDAU, 100 M trades day, 51K trades average, peak 10K trades, symbols, 10K stocks. Price updates can be frequent, maybe 1K update symbol during active trading, peaking at 10Ks for hot stocks.
That's a lot of updates.
It is. Orders data, 100 demo orders day, 50 bytes order at 5 GB day, or 2T by year just for basic order info. Price updates volume, this is massive. 10K symbols, 1K updates.
And 10 million updates per second flowing into the system during peak times.
10 million price updates per second.
Yeah.
Key insight.
Extremely high read volume for prices, moderate but critically important write volume for orders where consistency is king.
Got it. Core entities.
We need a user entity, user ID, name, maybe available funds.
Right.
A symbol entity for the stock ticker and name. User, symbol.
The order entity is complex. Ordered, user ID, symbol, order type, market limit, position, buy, sell. Price incense, use integers for money. Num shares, status, pending, submitted, filled, canceled, failed. And critically, external order to the ID assigned by the actual stock exchange.
Mapping our internal order to the exchange's order.
Crucial for tracking. And finally, a trade entity representing an actual execution. Trade ID, symbol, price incentive executed at, num shares executed, and which ordered, our internal one, it fulfilled or partially fulfilled.
User, symbol, order, trade. Yeah. API interface.
Typically RESTful API secured with something like JWT. You'd need get symbol name to fetch the live price for a stock.
That price.
POS order to create a new market or limit order.
Place order.
Delete order to attempt to cancel a pending order.
Cancel order.
And get orders to view the user's own orders, likely with pagination.
View orders. Seems standard. Now, the data flow. This sounds like it involves multiple systems, including external exchanges.
It absolutely does. Let's trace price updates first. This is usually a push flow. External exchange provides a data feed. This feed is often ingested into Kafka first to act as a reliable buffer. A trade processor service consumes from Kafka, updates a fast cache, likely Redis, with the latest price. A symbol service reads from Redis, pushes the update to connect to clients, probably using SSE.
Exchange Kafka Pascal process Redis symbol service Dorga SSE Tinus.
A pipeline.
Exactly. Optimized for low latency fan out. Now, order creation is different, more transactional. Client sends POS order API gateway order service. First writes a pending order record to a reliable database, probably Postgres for ACID guarantees. Then it submits the order to the external exchange via their API, gets back the external, order it out, stores this mapping in maybe DynamoDB for fast lookups later, updates the order status in Postgres to submitted response to the client.
Wow. Okay. Right. Pending locally, submit externally, update mapping and local status. More steps involved. Many more, and consistency is critical. Order cancellation is similar. Client API Gateway Order Service updates status in Postgres to pending cancel, sends cancel request to external exchange, gets confirmation updates Postgres status to cancel response to client.
Okay. And viewing orders.
Order listing is simpler. Client API Gateway Order Service queries the Postgres database user shard, returns the list to the client.
So the high-level design is definitely microservices talking to each other, databases, caches, and external exchanges.
Absolutely. A microservices architecture with a pub-sub model, Kafka Redis, for the high-volume price updates, and partitioned, consistent databases like Postgres for the critical order management.
Key component.
Client apps, API gateway, the symbol service, price subscriptions, the order service, order logic exchange sync, the trade processor, consuming exchange feeds, multiple databases, Postgres for orders, Redis for price cache, DynamoDB for external ID mapping, Kafka, buffering feeds, and the external exchanges themselves.
Quite a few moving parts. Why those specific database choices?
Postgres for orders because you need ACID transactions and strong consistency. It can also be partitioned effectively, maybe by user ad. Redis for prices and caching because you need extreme low latency reads and its pub sub is efficient. DynamoDB for the external ordered mapping because you need very fast key-based lookups, give an external ID, find our internal ID. And Kafka for the trade feed because it's a durable, scalable message queue ideal for buffering high-volume ordered data streams. #tag 8 deep dives.
Okay, deep dive time. First, scaling those live price updates. You mentioned 10 million updates per second potentially flowing in. How do you get those out to millions of users under 200 meters?
It requires a highly optimized pub-sub and fan-out architecture. The sources suggest using Redis pub-sub. You could have a specific Redis channel for each stock symbol, e.g. symbol.pubsub.aapl.
A channel per symbol? Who publishes? Who subscribes?
The trade processor service, consuming from the Kafka feed, publishes the price updates to the relevant Redis symbol channel. The symbol service instances subscribe to the Redis channels for the symbols their connected users are currently interested in.
So the symbol service gets the updates from Redis. How does it get them to the client?
It maintains a mapping for this symbol, which user rides are currently watching it and connected to this specific symbol service instance. It then pushes the update out to those users via server send events, SSE, which is efficient for this unidirectional push.
Okay, SSE again. How do you scale the symbol service and Redis itself?
You shard the symbol service, probably by user ride, so each instance only handles a subset of users and their subscriptions. Oh, for example, maybe 100 instances. Use a Redis cluster, sharded perhaps by symbol, to handle the massive pub-sub load. For example, 10 shards, each capable of maybe 1M OPSEC. You need load balancing for the incoming SSE connections, often using sticky sessions, consistent hashing based on user ride, or maybe even symbol, to try and keep clients interested in the same symbol connected to the same symbol service instance if possible, though the Redis pub-sub handles the cross-server broadcast anyway.
Sticky sessions help optimize, but Redis handles the core broadcast. Any other optimizations?
Yes, you can batch updates slightly, for e.g. send updates every 10 meters instead of instantly, to reduce network overhead. And you need a heartbeat mechanism to detect inactive clients and stop pushing updates to them, saving resources.
Makes sense. Back of the envelope numbers here.
Quick check. 10 million updates ESIC total, 10 Redis shards. 1 million updates X per shard, well within Redis capabilities. Fan-out bandwidth could be significant. 20 million users, maybe 10 symbols watched, 1 KB per update message. 200 milliburbs of outbound traffic just for price updates. Needs hefty network capacity.
Wow. Okay, next challenge. Tracking order updates and synchronizing our internal state with what actually happens on the external exchange via that trade feed. This seems complex.
It is. The key is reliably mapping the exchange's actions back to our internal orders. The solution involves that metadata store using DynamoDB. When our order service successfully submits an order to the exchange responds with its own unique ID for that order, external ordered. We immediately store this mapping. External ordered, usered, in DynamoDB. Why DynamoDB? Because we need very fast O1 lookups based on the external ordered later.
Okay, mapping stored. Now the trade feed comes in.
Right. The feed from the exchange containing actual executed trades flows into a Kafka topic, for example, trades, likely partitioned by symbol for ordered processing per stock. A trade processor service consumes messages from this Kafka topic. Each message contains details of an executed trade, including the external order it corresponds to.
Ah, the link.
Exactly. The trade processor takes the external ordered from the trade message, does a quick lookup in DynamoDB to find our internal ordered and user aid. With that information, it then updates the status of our order record in the main Postgres database in the correct user id shard, marking it as partially filled, fully filled, etc., and potentially creating a trade record.
So Kafka buffers the feed, DynamoDB provides the fast mapping, Postgres stores the consistent order state.
Precisely. You need robust state management for the orders, pending, submitted, partially filled, filled, canceled, failed, and logic to handle partial fills correctly by updating the remaining numshares on the order.
Back of the envelope for this flow.
10K trades peak, 1K B trade, 10 millibees ingress for Kafka. 10K lookups against DynamoDB easily handled. 10K writes to Postgres. This is demanding but manageable if Postgres is properly partitioned by user I. For example, 10K writes 100 shards, only 100 writes per shard.
Okay, feasible with partitioning. Final, critical piece, ensuring order consistency, especially despite failures. What happens if the system crashes right in the middle of placing or canceling an order?
This is where careful workflow design and recovery mechanisms are vital. Let's re-examine the create order workflow. 1. Order service writes a pending order to the user's shard in Postgres. 2. It synchronously submits the order to the external Exchange API, waiting for the response containing the external ordered. 3. Immediately upon getting the external ordered, it writes the mapping to DynamoDB and updates the order status in Postgres to submitted. 4. Only then does it respond success to the client.
Okay, multiple steps that need to succeed atomically almost.
Yes, and the cancel order workflow is similar. Update Postgres to pending cancel, send cancel to Exchange, get confirmation, update Postgres to canceled. The critical failure window is if a crash happens after the order is successfully submitted to the Exchange, step 2, but before our internal state, Postgres DynamoDB, is updated, step 3.
The order exists externally, but we don't know about it or think it's still pending internally. How do you fix that?
You need a cleanup job or reconciliation job. This is a background process that runs periodically, every minute. It scans the Postgres database for orders that have been stuck in pending or pending cancel status for an unusually long time, for example, 5 minutes.
Finds potentially orphaned orders.
Exactly. For each stuck order, the cleanup job uses the internal order details, like a client-generated order ID often sent during submission, to query the Exchange's API directly. What is the actual current status of this order? Based on the authoritative response from the Exchange, the cleanup job then updates our internal Postgres state accordingly, e.g., mark it as submitted, filled, or canceled if the cancel went through.
So it reconciles the internal state with the external reality for any orders that got stuck during processing failures.
Precisely. It's the safety net that ensures eventual consistency with the Exchange, even if synchronous operations fail midway. It combines ACID guarantees locally, Postgres, fast lookups, DynamoDB, and this crucial asynchronous reconciliation job.
Wow. Okay, that's incredibly thorough. Finally, let's shift to something maybe a bit more relatable day-to-day for many people. Fitness tracking apps like Strava. How do they keep up with millions of users tracking runs, rides, often in areas with spotty or no network? This raises that important question. What happens when your users are literally off the grid? Hashtag Karen. Designing a fitness tracking app like Strava.
Right. Strava presents unique challenges, especially around connectivity. Functionally, users need to be able to manage their activities, start, pause, stop, and eventually save their runs or rides.
The basic activity lifecycle controls.
During the activity, they need to see real-time data displayed on their device, their current route on a map, distance covered, elapsed time,
Instant feedback while exercising.
and after they're done, they need to view the details of their completed activities and also see the activities of friends they follow, enabling that social aspect.
View history, view friends' activities. Got it. Non-functional requirements must be interesting here due to the mobile, often offline context.
Very much so. High availability is important. Users want the app to work when they start their workout. But interestingly, availability is often prioritized much higher than strong consistency for individual GPS points during the activity.
Meaning, it's okay if the sync is delayed as long as the app works locally.
Exactly. Which leads to the next crucial requirement. The app must function in remote areas without network connectivity. offline capability is non-negotiable for a GPS tracking app.
Can't stop tracking just because you lose signal.
Right. It also needs to provide accurate and up-to-date local statistics, distance, time, pace during the activity, calculated on the device itself. And finally, Scale the Backend needs to eventually handle the data from potentially 10 million concurrent activities happening globally.
10 million people running and cycling at once.
Yeah.
That's still a lot of data eventually hitting the servo. What does the capacity estimation look like for storage?
Basic metadata per activity, type, duration, user, might only be around 100 bytes. The real cost is the route data, the GPS points. For a 30-minute activity, recording GPS every, say, 3 seconds gives you about 600 points. Each point, latitude, longitude, timestamp, maybe accuracy, is roughly 24 bytes.
So 600 points, 24 bytes.
Comes out to around 15 kilobytes of route data per activity. Now multiply that by a hypothetical huge number of activities per year, say 36.5 billion globally, and you're looking at 547.5 terabytes of route data annually. Storage efficiency and tiering become important.
Half a petabyte a year just for routes. Wow. Okay, core entities.
Pretty straightforward.
Yeah.
User, profile info settings. The activity itself, run, ride, start, end time, distance, duration, and critically the route data.
Route data could be embedded or separate.
Could be a field within the activity entity, often stored as a list or array of GPS coordinate timestamps.
Yeah.
You also need a friend entity or relationship to manage the social connections for sharing activities.
User activity with route. Friend, got it.
Sure.
API interface.
Needs to support that activity lifecycle. POC activities to create a new activity when the user hits start.
Okay.
To update the state, pause, resume, complete, you'd use pattchactivities.activity.id. pattch is efficient here as you're only changing a small part of the activity record state.
Makes sense. What about sending the GPS points?
This is key. While you could have an API like pattchactivities.activity.id to send updates with new coordinates and distance, the critical insight from the sources is that you don't typically call this repeatedly during the activity. We'll get to why in the data flow.
Intriguing. Okay, what about viewing activities?
Standard GetT requests. GetTactivities.modi, user friends and paid size for fetching lists, your owner friends with pagination. And GetTactivities.activity.id to get the full details, including the route data, for a specific completed activity.
Okay, now let's trace that data flow, especially the law of tracking part.
Activity lifecycle, start, pause, stop, save. User hits start. Client at POS activity service creates a basic activity record in the database, returns a new activity ID. Pause resume client sends pattchactivities.activity.id with the new state, paused, resumed. Save, Plasson sends pattchactivities.activity.id with the state complete and all the accumulated data, route, final stats.
How is pause time handled accurately? Just start end times isn't enough.
Good point. Instead of just start end, the app or backend should maintain a log of status timestamp pairs for the activity. Start, T1, pause, T2, resume, T3, stop, T4. The actual elapsed moving time is calculated by summing the durations between status changes, excluding the paused intervals, T3, T2 in this example.
Calculating moving time from the status log. Clever. Now, the crucial part, viewing live activity data, route, distance, time, during the workout. How did that work without constantly hitting the server?
This is the core insight. It's handled almost entirely locally on the client device. The client app uses the phone's native GPS capabilities, core location on iOS, Google Location Services on Android, to record GPS coordinates periodically. AG every 2 seconds for biking, 5 seconds for running.
Okay, app gets GPS points locally. Then what?
Crucially, it does not send these individual points to the server in real time. The logic for calculating distance between points using the Haversine formula, summing total distance, calculating elapsed time using that status log, deriving pace state, all of this happens locally on the client device.
Wow, so the real-time display is purely local calculation.
Yes. This provides the most accurate, up-to-date stats to the user, works perfectly offline, and massively reduces the load on the back-end servers during the activity itself.
That's a huge architectural decision. What about viewing past activities or friends' activities?
That's standard backend interaction. Once an activity is completed and synced to the server, clients use those GT activities for lists and GT activities.activity.id for details, endpoints, to fetch the data from the backend database. The friends relationship might be stored in a table, user-derived, friended, often made bidirectional for efficient lookups, Find friends of user X or check if user Y is a friend of user X.
Okay, so the high-level design heavily emphasizes client-side processing for live data, interacting with an activity service, and a database primarily for completed activities and social connections.
Exactly. Time calculation handles pauses via stay logging. The backend deals more with storing historical data and serving requests for completed activities rather than handling millions of real-time GPS pings. Hashtag tag 8. Deep dives.
Okay, let's dive deeper into that core requirement, supporting offline activity tracking. How is that seamless experience achieved?
The solution is local data recording and deferred synchronization. As the user exercises, the app records all the activity data, GPS points, timestamps, status changes, directly onto the client device. This might be buffered in memory initially, but it's periodically persisted to local storage, maybe core data or user defaults on iOS, room database, or shared preferences on Android to prevent data loss if the app crashes.
So it's saved locally first. When does it get to the server?
The sync strategy is key. The primary approach is to sync the entire accumulated activity data back to the server in a single, larger request, only when the activity is marked as complete by the user and the device has network connectivity.
Upload once at the end. What if it's a really long activity, like a multi-hour hike?
For very long activities, the app might implement chunking, breaking the data into smaller pieces for upload. For durability, a more robust app might have a background sync mechanism that periodically tries to upload chunks of data whenever network connection becomes available, even if the activity isn't finished yet. The locally stored data is only deleted after the server successfully confirms receipt.
So local persistence first, then opportunistic or final sync? How does this offline-first approach impact scaling to 10 million concurrent activities on the backend?
It makes backend scaling significantly easier. Because the backend isn't receiving a constant stream of GPS pings from 10 million devices, it receives maybe 100x fewer requests overall, as data is typically sent only once when the activity completes.
Huge reduction in write load.
Massive. So for scaling strategies on the backend, database sharding is still relevant for the stored activity data, perhaps partitioning by activity completion time, as most queries will likely be for recent activities. Data tiering is also crucial given the potential storage volume move older activities to cheaper warm or cold storage, like S3 Glacier.
Keep recent activities fast. Archive old ones.
Right. Caching, example Redis, can be introduced for frequently viewed completed activities or user profiles, but it's perhaps less critical initially compared to systems with constant high read traffic, because the read load for past activities might be more spread out. The activity service itself still needs to scale horizontally to handle the uploads and read requests, but it might not need to be broken down into many fine-grained microservices, given the reduced real-time load.
So offline tracking simplifies the real-time back-end scaling problem significantly. Okay, but what about supporting real-time sharing of activities with friends? If the user is offline, their friends can't see them, but if they are online, people often want to see live progress. How does that work?
Yeah, good point. If you want to enable live tracking for friends, you have to reintroduce some server communication during the activity, but only when the user has connectivity.
So it's an optional, connectivity-dependent feature.
Exactly. The solution: reintroduce periodic server updates with polling by friends. While the user's own display relies on local data, if the device is online, the app can send location updates, maybe just lat.long timestamp, to the server every, say, 2 to 5 seconds. The server persists these somewhere temporary, maybe a cache or a dedicated table.
Okay, server gets periodic updates if online. How do friends see it?
Friends who are viewing the live activity would then poll the server endpoint for that activity every few seconds to get the latest known location points. Polling is often effective here because the update intervals, 2 5s, are predictable, and absolute up-to-the-second precision isn't usually critical for a friend watching. A delay of a few seconds is perfectly acceptable.
So local for self, periodic push if online for server, polling by friends to view.
Yes. An enhancement mentioned is smart buffering on the friend's viewing client. Intentionally display the location data lagged by maybe 1-2 update intervals, for example, 5-10 seconds behind real time. This smooths out the movement and avoids jerky jumps on the map, creating a more continuous animation, even if updates arrive slightly irregularly.
Clever smoothing trick.
Yeah.
Okay, one last feature. Exposing a leaderboard of top athletes. Curious about most distance run this week. How is that typically handled?
This brings us back to Redis sorted sets. They're perfect for leaderboards. You'd use Redis, an in-memory data store for speed, to maintain sorted sets, perhaps like leaderboard.run.weekly.global.
What are the members and scores?
User IDs would be the members, and their score would be the relevant metric. AG table total distance run in meters for the week. When a user completes and saves a run, the backend service updates their score in the Redis sorted set, for example, using ZINCRBY.
Incrementing the score. How do you get the top N?
Querying the top N is incredibly efficient using commands like zrvrange for highest scores first. It's much faster than querying and sorting in a traditional database.
What about filtering, like leaderboards per country?
You'd simply maintain separate sorted sets for each filter context. Example, leaderboard.run.weekly.usa, leaderboard.run.weekly.gbr. When a user saves an activity, you update all relevant leaderboards they belong to, global, country, maybe age group. You'd also likely implement caching on the API layer that serves leaderboard data, as these can be frequently accessed endpoints. And what's really insightful looking back across all these different systems is how certain architectural patterns just keep reappearing, don't they? Message queues like Kafka or SQS for decoupling, durability, and buffering. We saw that in notifications, options, payments, even LeetCode submissions.
Yeah, the queue is everywhere. And the trade-offs between consistency and availability came up constantly. Strong consistency needed for payments and orders, but eventual consistency or availability prioritized for live comments or even Strava's offline tracking.
Exactly. And the strategic use of caching with Redis for everything from leaderboards to session data to metadata lookups is almost universal for achieving low latency at scale. Plus techniques like sharding databases, whether it's Postgres for orders or NoSQL for metadata.
And that clever use of client-side intelligence in Strava, offloading the real-time calculations, fundamentally changing the back-end load profile.
It really highlights how system design isn't just about the backend. It's about the entire distributed system, including the client. So thinking about all this, it raises an important question for you, the listener. How might these core principles, prioritizing availability versus consistency, managing async flows with queues, leveraging caching, thinking about client-side roles, apply to a system you use every single day? Maybe you use an app or website without ever realizing the intricate design decisions and trade-offs happening behind the scenes.
Because once you start seeing these patterns, like the use of PubSub for fan-out or OCC for managing bids, you really can't unsee them. It's almost like getting X-ray vision for the digital world around us. This deep dive has been quite a journey through some incredibly complex systems. We really hope it's given you that shortcut to being, well, incredibly well-informed. Thank you for joining us on the deep dive. What else are you curious about?